All right, how's it going, everyone? My name is Justin Wu. I am a asynchronous student. And just to get right into it, the paper critique that I did was on an adaptive traffic signal control system, specifically a system called ACS-Lite. All right, so to start off with some background, for traffic signal control systems, I'm going to go over two of the main ones that are used currently, and they are the pre-timed and actuated. So what pre-timed basically is green time, and the splits for all approaches at the intersections are fixed. And when I say fixed, I don't mean fixed for the entire day. I mean fixed for let's say that specific AM peak hour, for example. So during that AM peak hour, all approaches will have dedicated green time that does not change. Um, and this is good for consistent traffic flow, and it's also beneficial for smaller traffic volumes. For actuated, we have two different types. We have semi-actuated and then fully actuated. Um, so what semi-actuated is there's basically vehicle detectors on the minor roads of the intersection, and the main road does not have any detectors. So what happens is the main road gets green time, and it will continue to get green time until a vehicle is detected on the minor road. So if no vehicles are detected, the main line will continue to get green time. And when the minor road detects a vehicle, that's when the main line will get red time, and the minor road gets green time. And this is different from fully actuated because in this case, even the main lines now have vehicle detectors. And so this is different from pre-timed because in pre-time, you could have no vehicles on side streets or the minor roads, but they still get green time, um, just because it's fixed, right? And again, in this case, actuated is good for fluctuating volumes, and also larger traffic volumes, just because especially during, let's say, peak hour, at a intersection with a high traffic volumes, you don't want the vehicles on the main line to be waiting there, while there's no vehicles on the minor roads, right? So for efficiency purposes, actuated is better for fluctuated volumes. All right, so now to introduce what an adaptive traffic signal is, which is what this study is about, and specifically ACS Lite is so it basically operates in real time and it adjusts signal timing to meet current traffic demands. Um, and in this case, there's actually no need for a central computer system. Whereas for the pre-timed and the actuated that you saw before, both semi and fully actuated, there's a central computer system that controls and you know when a vehicle is, for example, detected, that's when they get green time, right? In this case, everything can be operated from a laptop actually. And ACS Lite is actually already demonstrated in Ohio, Texas, and Florida. So to quickly go over the study corridor, so study corridor is in Wolf Road, and Wolf Road is located in Albany, New York. There's 9 intersections, and the reason it was chosen is because it is a congested urban corridor. So, also to go over the project flowchart and how this study was conducted. As you can see, we have a list of tasks on the right. Um, and to quickly go over the measures of effectiveness that were used, MOEs. So travel time was collected, intersection delays were collected, as well as average speeds, queue lengths, number of stops, duration of stops, fuel consumption, and carbon footprint. And then I have here basically just who is in charge of implementing each system, or each task. So, for example, ACS Lite, that was implemented by Simons. Travel time and detection, that was implemented by Senses. And then any communications between field laptops and remote users was Anise and Associates. So, So now going into the limitations and delays. So there were a lot of limitations and delays that caused, the project to take a little longer than expected, just because this was the first time the ACS Lite was being tested in the field, like on an actual study corridor. Um, and at least in the state of Virginia, right? So, no, first there was a limitation in the control software, and this was because it was not the most up to date in terms of the existing control software. Um, so the control software SEPAC was incompatible with the existing controllers and timing plans, and this required software development and updates in order to make sure both were compatible. There were also I/O mapping issues, and what I/O mapping issues, what that basically is, it's assigning a controller input and output addresses to traffic light functions and sensors. Um, and then there were also pedestrian options, but ACS Lite, the version that was used at the time, was not able to use, and it was not able to accommodate advanced walked operation. There are also limitations with the cycle time. So this was actually one of the limitations that was not able to be addressed. And as you can see later, it causes issues in results. But the version of ACS Lite that was used was actually unable to modify the cycle length to meet traffic demands. So this was at one of the intersections. It was Sand Creek Road, where the left turns were actually given half the green time in the after scenario compared to the before scenario. So as you can expect in the after scenario, the queues were much worse, and delays as well. There were also software issues, um, and this didn't directly impact any results, but just as as something to note with installing, a new um, traffic signal control system, the signal at Albany Shaker went into flashing mode during the transition. So to go over the before scenario, data was collected before ACS Lite was installed and implemented, just to see how the corridor was currently operating. And to summarize, the delays in queues were large, and they were specifically large at Albany Shaker and Sand Creek intersections. So, as you can see, Albany Shaker was operating at an LOSE in the PM peak with a delay of 57.2 seconds. So that is LOSE is not good. Um, as well as the queues, there were very long queues on Old Wolf Road. As you can see here, a little over 22 vehicles in the AM peak. Um, and in addition, fuel consumption was also collected, and that actually increased, as well as emissions throughout the day. So, in addition to delays and queues, average travel time and average stop duration was also calculated and found. So the northbound movement had the largest travel time of 335.8 seconds in the PM peak. And even then, it looks like the travel time was roughly the same. And the travel time is the time from one end of the corridor to the other. And the average stop duration was the largest in the PM peak, where it was 97.1 second. So um, and travel speeds are also inversely proportional to travel times, stop durations, and number of stops, which makes sense. As travel times are increasing, as there's more stops and the stops are longer, that means there's probably more congestion, and with more congestion, that means that travel speeds are lower. So for the after scenario, after ACS Lite was implemented, data was collected again, and as you can see, the two intersections that operate the worst are still Albany Shaker and Sand Creek, but now they operate even worse. Um, and Albany Shaker before was operating at an LOSE in the PM peak, and now it's operating at an LOSF with 105.8 seconds. Um, and the Qs are also roughly 21 in the AM peak. And again, there's also an increase in fuel consumption and emissions throughout the day, just similar to what we saw for the before scenario. So in addition, average travel time, the largest was in the northbound movement at 364 seconds. Average stop duration was 124.9 seconds in the PM peak, also for the northbound movement. Um, and the reason, so the number of stops was also collected, but the reason I decided to focus on duration of stops um, was because signals can be coordinated well. So you could stop 5 6 times throughout the study corridor, but if you're stopping for a second or 2 seconds at each stop, that's different from stopping one or two times, but stopping like we see here like 125 seconds, right? So I decided to focus more on the average stop duration instead of the number of stops in this specific case. So now moving on to the comparison. So we see, like I said before, that the delay in queue lengths at Albany Shaker intersections worsened. You can also see this in the figure here. Basically, a lot of intersections improved. As you can see, delays decreased to less than zero, but delay at Albany Shaker increased greatly, especially during the PM peak. And again, Albany Shaker is one of those boundary intersections that I mentioned beginning. And so the reason you guys might have seen in some cases, delays or queues during the weekend on Saturday were the longest. And the reason I didn't point those out were because ACS Lite was not active during the weekends. Um, so I didn't take into account the weekend data when comparing the two. Um, and also there was an increase in fuel consumption and emissions for southbound traffic specifically, and then a decrease for northbound traffic. So again, continuing with the comparison, travel time actually decreased for most movements. Um, as you can see here, most of the movements are in this negative under zero area. Um, Duration of stops actually increased for most movements, as you can see here. Most are above zero. Um, and to note, the reason why northbound right and southbound left movements are not focused on as much in this case is because the sample size in the after scenario was much smaller than that in the before scenario. So it's 11 vehicles for the northbound right and 9 vehicles for the southbound left. The after scenario compared to 47 and 47 in the before. Um, so northbound right, that would be this green. As you can see, huge changes and huge differences. And then southbound left as well. It's red here. So to go over the cost benefit analysis that was conducted. So what was taken into account was the traffic volumes, delays, and fuel consumption and emissions that were used. And for each of these, the data was combined for each intersection and approach to reflect the entire corridor. So all traffic volumes throughout the entire corridor were combined as well as the delays. And the data was converted to monetary values. And the monetary values you can see at the bottom of this table, how the cost was guy and the sources that were used for this. Um, and the total project cost was actually at roughly $570,000, with roughly $300,000 from New York State DOT, and then roughly $270,000 shared by RPI and industry partners, which are basically anyone else involved in this project. So when doing the cost benefit analysis, there was two different types that were considered. So the first one was the total cost and differences for the corridor. This included all intersections. And as you can see here, the total cost was actually negative 1,000. Um, this means that there was a loss of roughly $1,000 per day. Whereas in this next table, the same thing was done, but now Albany Shaker intersection, the one that was performing the worst in terms of operations, was excluded. And in this case, there's actually a benefit of roughly $145 per day. So looking at the benefit cost ratio and comparing that to the total project costs, as well as just the cost from New York State DOT, if we want to break even, it would take roughly 15 years to break even using total project costs. But if we're just considering the cost that New York State DOT paid, it would take roughly 8 years, which is half. So these are some recommendations that were actually stated in the report. So it was said to explore an integrated corridor management approach and consider route diversion, as well as exploring, a larger network and coordination between freeways and arterials. Um, and finding ways to restrict flow into the system, and this would hopefully address boundary intersection operational issues that we saw at Albany Shaker. Um, so what they're basically suggesting is potentially to use this red dotted line as the boundary for the study instead of just this blue, which is what was used for this report. And maybe seeing if coordination between you know any any off ramps or any other signals that we can't see from here at this um, freeway, and seeing how that could impact these boundary intersections that are causing huge issues, and then maybe finding ways to restrict flow into that system, whether that be rerouting vehicles somewhere else or just finding other ways to improve operations at those boundary intersections. So in terms of the paper critique, we have 6 vehicles used in the before scenario compared to 3 vehicles used in the after scenario, and this was when they're collecting travel times. And as someone that has collected travel time, I can say that especially when you're given an hour to do it, whether that be AM peak hour or PM peak hour, 6 vehicles compared to 3 is a big difference in terms of you know the amount of data that can be collected, especially for a long corridor where it takes a long time to travel from one side to the other. Um, so you know, knowing that either just using 3 vehicles in the before scenario or you know, finding ways to use the same amount in both. Also, I noticed that there were no right turn queue lengths or delays in the report. And in theory, this makes sense because um, you know, right turns are usually yield or they right turn vehicles go when they find gaps. If they don't have the green, um, there are situations where there's no right turn on reds, and there is queue lengths or delays, and that was not specified in the report. So, and I felt like this was necessary, especially because at the end, we were um, adding all the delays together when doing the cost benefit analysis. So, if there are right turn queues, especially at those boundary intersections that are operating pretty poorly, I felt like it was necessary to include. Um, and also, just the fact that weekend data was not included, or just the fact that weekend data was not collected because ACS Lite was, or it was collected, but ACS Lite was not active. I felt like maybe that time spent collecting that data or adding that in the report could have been maybe used or something else. Just because I feel like um, weekend data was not used as much. There's even specified in the report that weekend data was basically overlooked. So for Albany Shaker intersection, and how it was not included in one of the tables for the benefit cost analysis, I felt like, you know, if anything, that should be the main focus, because that's where all the congestion is happening, right? Um, and if that problem is fixed, then ACS Lite can be better proven to be used in other corridors, right? But because it was operating so poorly, I feel like we can't just do a benefit cost analysis without including that intersection, right? So that was something that I noticed, that I feel like, instead of trying to move away from the intersection that was causing the most trouble, maybe focus more on it. Um, and so the primary goal stated in this report was to document the experiences and key lessons learned from the deployment and evaluation regarding how an adaptive control system can be deployed, the advantages and disadvantages of the system, and whether it is suitable for use in other corridors in New York State. So is this goal met? I do believe that there's many lessons on the implementation of an adaptive control system, specifically ACS Lite, in terms of software updates, um, and any pedestrian issues that we mentioned earlier in the limitation section. That can be fixed for next time, and that was simply just because this is the first time that ACS Lite was used in a study corridor in Virginia, right? Um, And then also there was some information that we got for in terms of advantages and disadvantages of systems. Same thing going back to limitations. But I would say one thing that was not met was deciding whether or not it is suitable for use in other corridors in the state of New York. And I feel like that is because you know, I feel like a larger network, like we talked about in the recommendations, would have to be considered. To see if if that issue at the boundary intersections could be resolved, and if that is resolved, there is a way to fix that. Then I feel like we have a better understanding of whether or not it's suitable for other corridors in New York. Um, but if not, I feel like it's we don't have enough information to make that decision. And yeah, so if you guys have any questions, I believe there's going to be a way for you to ask questions, whether that be like a discussion or maybe. But yeah, feel free to reach out if you have any questions or want more clarification. And then being said, I have my sources here. Yeah, that was it. And I appreciate you guys for listening.